tour series for 2022. I'm Aaron Slepkov, and I'm pleased to host this talk from the Department of Physics and Astronomy at Trent University. We had hoped to be able to have this talk in person at Peterborough and stream across Canada, but COVID logistics required that we move these lectures online. The lecture tour is sponsored by the CAP Foundation and the Canadian Association of Physicists, a national network of about 1,700 physicists working at universities, companies, and research institutions across Canada. The CAP works on behalf of Canadian physicists to support physics research and education and sponsors a number of physics activities, including this lecture tour and national research conferences. The CAP also delivers a number of programs for undergraduate and graduate students, research conferences, physics scholarships and prizes, and a student advisory council. If you have not already joined the CAP, please consider becoming a part of Canada's largest network of physicists and physics students. It's free for undergraduate students and the first year of membership for graduate students as well. Today's talk will comprise a 45-minute presentation followed by 10 minutes for questions. If you would like to pose a question to Dr. De Sousa, you can type it in the chat at any time and I'll pose it to the speaker at the end of the talk. Following the talk today, you'll have an option to join a breakout room where you can speak directly with the speaker, ask additional questions about his research or about related career paths. Now, it gives me great pleasure to introduce today's speaker, Professor Rogério de Sousa from the Department of Physics and Astronomy at the University of Victoria. Professor de Sousa's research focuses on the physics of materials and devices with applications to quantum computing and spintronics. Today, Professor de Sousa will present his talk titled From Quantum Mechanics to Quantum Computers. Welcome, Professor de Sousa.
Thank you, Aaron, for this nice introduction. And also a big thanks for people at CAP and at Trent University for organizing this lecture series. So I'll talk to you about, I'll give an introduction to what's going on in quantum computing, and I'll try to connect the ideas of quantum computing to what we all know about quantum mechanics. And in particular, I'll try to answer the question, how can quantum computers be built and why are they so efficient for some applications? So I'd like to start with territorial acknowledgement. So I acknowledge and respect that I'm speaking from the land of the Lekwungen peoples, where University of Victoria stands. This is a picture of the first people's house at University of Victoria. And in the context of science and technology, it's very important for us to democratize knowledge and to share our discoveries with indigenous peoples, particularly indigenous youths and also K-12. If you're interested in this topic, I suggest you take a look at this nice program, Diversifying Talent in Quantum Computing, which is run by my colleagues at UBC. There are lots of volunteer opportunities and also lots of materials, games, and apps for you to download and to play with. So I'll start my discussion talking about waves. You probably know that light is a wave. Now the question is, how do you prove that light is a wave? Well, you do by using a two-slit experiment. It's also called Young's double slit experiment. And the idea is that you shine light from one slit and then you spread out from two slits. And what you get on the screen is an interference pattern. So what's happening is that light is being emitted from both these slits and interferes with itself. And that proves that light is a wave. You can do the same experiment with waves in a pool of water. For example, if you take a look at this video here, if you have two slits, you send parallel wavefronts and you get an interference pattern. So basically, when the waves are adding to each other, you have a maximum amplitude. When the waves are subtracting each other, you have no amplitude. So this pattern proves that light is a wave. Well, it turns out that about 100 years ago, people discovered something quite amazing about matter. So that's not about light, but about particles with mass. It turns out that particles with mass, such as an electron shown here, also behave like a wave. And nowadays we can do an experiment where we can actually send one electron through a double slit, just like we did the experiment with light. So you can use an electron beam. An electron beam is just like the old school TV, those big TVs, those big heavy TVs from 10, 20 years ago. And when you send one electron at a time, if you have a detector here that clicks when the electron hits the screen, you will create dots on the screen. And as you send more and more electrons, you see that the same interference pattern is created. Now, what this experiment proves is something quite remarkable. It proves that even a single electron being sent through this screen actually is able to interfere with itself. Now, if you like to think of electrons as a point particle, consider the following. What if you put a detector at each slit? Because I suppose that it's quite surprising that the electron goes through both slits at the same time. A single electron going through both slits at the same time, that's quite strange, right? But if you put a detector, then you can find out which slit the electron went through. But if you do that, the experiment changes completely. What you get is a classical interference pattern. The wave interference pattern is destroyed. And this is the typical thing about quantum mechanics, is that the electron behaves like a wave until you try to make it behave like a particle by putting detectors here. When that happens, the wave collapses into a state that has a well-defined trajectory. So quantum computing will exploit this property of interference and destruction of interference by measurement, right? So just for you to know, as you probably learned in your quantum course, this interference pattern here is a probability distribution that you can calculate. So the question then is, what happens when you confine these waves in a finite region? Well, you know the answer for a string, such as a guitar string. So you can confine a guitar string about these two regions, and what you find is that the frequency is quantized. It's quantized in such a way that the length here is half of a wavelength, right? So that's the lowest frequency we can get. You cannot get any frequencies lower than that. You can increase the frequency a little bit by fitting two half wavelengths in that distance of confinement. And you can increase it even further by fitting 3/2 of wavelengths, right? The frequency is a velocity times 2 pi over lambda here. So the frequency, so the wavelengths are quantized, therefore the frequency is quantized. That's called a standing wave. Now, in a classical wave, such as a string or even an electromagnetic wave of light, you have a particular wave equation. In quantum mechanics, we also have a wave equation, but that wave equation is a little bit different. But essentially, what happens is the same thing. If you try to confine an electron in, for example, a parabolic potential like this, that's the same as attaching a spring to the electron, right? So that's an electron glued to a wall through a spring, for example. You will get standing wave modes. You know, the details of the wave equation is different, but the essence is the same. You get a lowest frequency mode. So that's the probability distribution for this lowest frequency mode. And then a second lowest frequency mode, and so on and so forth. The energy levels, which are equivalent to the frequency quantization on the guitar string that I just showed you, they are equally spaced for the case of this parabolic potential. So this turns out to be h bar omega naught, where omega naught is the natural frequency of this, this spring. So these are the same energy scales. The energy levels are equally spaced. H bar is this very small constant that converts frequency to energy in quantum mechanics. So the point is that you can have standing matter waves of electrons and other particles in the same way that you have standing frequency modes for a guitar string. So, of course, you can do the same thing with an atom. So an atom is a proton. For example, hydrogen atom is a single proton with an electron orbiting around it. And the confinement of this electron is a Coulomb confinement. It goes as 1 over distance. And you can calculate the matter waves for that. And what you get are the energy levels for the hydrogen atom, right? So the standing modes now, they're 3-dimensional standing modes. For example, this is the fundamental mode here. We call it ground state, called 1s state. And the interesting thing is that now the energy levels are not equally spaced anymore. They're quite unequally spaced. In fact, you have a huge energy difference between the first excited state and the second excited state. Okay. So in a moment, you see that this is important for making a quantum computer because you want 2 separate excited, a ground and a first excited state that are not resonant with the other excited states in order to make a quantum computer, in order to make a quantum bit. So this takes me to the idea of quantum information and quantum bits. So you're probably all familiar with classical conventional computers. So where we represent data by either zeros or ones. That's, of course, a very efficient and well-developed technology, right? So all the data that we use in computers are zeros and ones. So bit strings like 0, 1, 0, 0, 1, 1, 0, 0. The idea of quantum computation is to define data using quantum mechanics. And in that case, you have other options. So if you take, for example, just as a simple example, the ground and the first excited state of this hydrogen atom, then you can have superpositions between 0 and 1. So if I call this state here the 0, the ground state, and this state the 1, then I'm also allowed to have mixtures between 0 and 1, just like waves. You know, waves interfere with each other. This creates an interference pattern between state 0 and state 1. And that turns out to be powerful. That's not the whole story. There's much more to it. Those quantum bits, they can also be entangled. And that's interesting because that's unlike anything classical. So what is entanglement? Entanglement is when you have 2 quantum bits that are strongly correlated with each other. For example, they could be in this state here, 0, 0 plus 1, 1. The consequence of this is that if you measure the first qubit, the second qubit, so if you measure this first qubit and you get a 0, the second qubit immediately collapses to the state 0 as well. So they're highly correlated. Those states cannot be made classically, and this is part of the reason why quantum computing is so different from classical computing. So how to make a quantum computer? So there are many ways to make a quantum computer. In fact, I should emphasize that there are many different technologies that have been shown to work, but not all the technologies are well developed right now. So here in this talk, I will mention two technologies that are very well developed, and you can actually run jobs, run quantum algorithms in these quantum computers. The first one that I'm going to talk about is the trapped ion technology, trapped atom technology. So what people can do is that they can trap single atoms. In that case, those are atoms of calcium in an electromagnetic trap. That's the electromagnetic trap here. And this is a picture of the atom. So you can see 1, 2, 3, 4, 5, 6, 7, 8 atoms. So you have 8 qubits. Those atoms, they're not hydrogen atoms. You can't do quantum computing with hydrogen atoms. Rather, you need something more complicated because you want to manipulate the states of the atoms. And for that, you need extra states. But here's the energy level for calcium. So you have a ground state. So that we'll call our qubit state 0. And then you have an excited state here. One of these excited states, we'll call it 1. And then you can use these other states to create transfers from 1 to 0 and 0 to 1. And you can do that coherently. So that's a very nice way of making a quantum computer. And right now we have 14, 15 qubits that work very well. They're very low noise. And there are companies already in the stock market who are promising to deliver these machines. So now the other technology, which is even more advanced, uses electrical circuits. So this is convenient because you can actually print electrical circuits and make artificial atoms with it. Now, the trick is that you have to cool down your circuit until it becomes superconducting. So it has to be at very low temperature. Now, I'm sure a lot of you have heard of superconductivity. So this is resistance as a function of temperature. When you lower the temperature below a critical temperature, and for aluminum, this is 4.2 Kelvin for aluminum wires, your aluminum becomes superconducting, so it has zero resistance. But it turns out that the big deal about superconductivity is not the fact that the resistance goes to 0. The big deal about superconductivity is that when you go below that critical temperature, your electrons, they act as a single quantum state. So you have 10 to the 20, a huge number of electrons that are coherent with respect to each other. So I like to think the superconductor as the laser of electrons. So the normal metal, the non-superconducting metal, is a light bulb. The superconductor is a laser, where, in the laser, the photons, which are the particles of light, they're all coherent with respect to each other. In the superconductor, the electrons are coherent. That means they show a phenomenon called macroscopic quantum behavior. And this is very nice because they're big, we can print circuits, and we can make artificial atoms with them. An essential ingredient is something called Joseon Junction. Now, the Joseon Junction is just an insulator between two superconductors. And what it allows you is it gives you the nonlinearity needed to design your artificial atoms and your qubits. So here's why Joseon junctions are important. So consider this circuit here. So here I have a current source. And I have the Joseon junction. So it's superconductor, insulator, superconductor, and I'm applying a magnetic field. The current will display exactly that same interference pattern that I showed you with the double slit experiment. So you can see that the Joseon junction gives you the functionality needed to manipulate your quantum states. So using this technology, IBM and Google are able to make quite large quantum computers with more than 100 qubits right now. And this is a picture of their quantum computer. So the first one is made by IBM. It's a 5-qubit quantum computer. In fact, later in our talk, I'll show you how to run quantum algorithms in it. You can do it yourself. It's public. You just sign up and you can submit your jobs to their quantum computers based in New York State. So the way this works is actually a combination of quantum theory and cell phone technology. So you have here the qubits. And the qubits are connected by coaxial cables. Those coaxial cables are called coplanar waveguides that transfer microwaves. And using microwaves, you can read out and manipulate the state of your qubit. Google's technology is very similar. There are some important differences, and this was the technology that they used to show quantum supremacy. So they used this kind of device to show quantum supremacy. This is a 9-qubit device. Quantum supremacy was with, I believe, 60 qubits. Actually, greater than 60 qubits. So let me explain how this technology works, because it's incredibly simple, actually. You can think of it as a quantum antenna. So the qubit is called transmon, but you can think of it as a quantum antenna. And literally, this is what I'm showing you here. It's the so-called 3-dimensional transmon, which is an interesting device on itself. And people are trying to make quantum computers with many qubits using this design. And here you can see that you have a copper box, and you're sending microwaves in and out. The qubit right here is literally 2 aluminum pads interrupted by a Joseon junction. Right. And what that gives you, it gives you a nonlinear harmonic oscillator where you can isolate 2 qubits. You see, if you didn't have the Joseon junction, you would have a simple harmonic oscillator. All the quantum energy levels would be equally spaced. And you can't have a qubit that way, because if you try to excite from 0 to 1, you end up also getting excited from 1 to 2 and from 2 to 3. But when you add the Joseon junction, the harmonic potential becomes slightly unharmonic. And now you can separate the qubit. And separate the qubit here. Right? And using that, so the IBM and Google technology that I showed you before, these chips here, they're literally the chip version of that. So they're, the 2-dimensional version of this 3-dimensional qubit here. So the way it works is that you send microwaves in, and the microwaves interact with this antenna, and they excite from 0 to 1, so on and so forth. And then when you want to read out, you send another weak microwave, and you look at the phase shift that is reflected from the device. All this is cell phone technology, microwave engineering, but it's microwave engineering at low temperature. There are other kinds of qubits. For example, consider the qubit that is made by D-Wave Systems, which is a company in Vancouver that I actually collaborate with. This qubit is also based on superconducting circuits, but it's a little bit different. It uses what's called SQUID technology. SQUID means superconducting quantum interference device. And what this is basically now a ring of superconducting metal interrupted by Joseon junctions. That way, when you apply a magnetic field or you couple the circuit to an inductor, you can manipulate the qubit. The potential that you get, the artificial atom that you get, is now a double well potential. And where the ground states, you probably saw this in your basic quantum mechanics course, are plus, so they are plus electrons rotating left plus electrons rotating right, or in the first excited state is electrons rotating clockwise minus electrons rotating counterclockwise over root of 2. So this is the qubit here. The thing about the D-Wave device is that its specific purposes, it only solves one problem. The problem is what we call quadratic binary optimization. Physicists call this the Ising problem with programmable interaction. So these are programmable. So the interaction between the qubits, so the states of the qubits, the states of the classical bits are either 0 or 1, but these become quantum at low temperatures. And you can program these parameters Jij and Hi. And this is nice because this maps into a bunch of optimization problems. Those are large quantum computers. They already have 5,000 qubits. This one here has 2,000 qubits, but they are not universal. They only solve a particular problem. You can program the Gi's and Hi's, but you can only solve the problem related to minimization of this energy. So what can you do with a universal n-qubit quantum computer? So this question here, in my opinion, answers why there's so much excitement, so much research funding, and even hype. But I want to give you a precise answer to that. So first of all, we should understand that, in a way, the power of quantum computing comes from the fact that you're dealing with an exponentially large number of states. So when you have n qubits, your Hilbert space, the amount of states that you have access to is 2 to the power n, and that blows up very fast, right? 2 to the power 100 is an enormous number, right? Now, what can you do? Now, the first thing that people showed back in the 90s is that you can factor large numbers. So you can write large numbers as product of primes. The best classical algorithm for that is it takes 2 to the power cubic root of n, right? So it scales almost exponentially with n. But the best quantum algorithm, which is a modified Shor's algorithm, takes only order of n squared log n. So now that's almost exponential speed up. You can also solve other interesting problems with this algorithm. For example, you can solve the discrete logarithm problem, which is a logarithm in group theory, and also a lot of other group theory problems that can be very useful. You can also break the security of the internet with that, and this is one of the reasons why people take quantum computing very seriously in the cryptography community. But you can also use quantum computing to devise cryptographic schemes that are 100% secure. I can tell you more about that in the discussion session. The other application is to simulate molecules and materials. So Richard Feynman famously talked about that a long time ago. So Feynman said, well, if you want to simulate quantum systems, that's clearly a very hard thing to do, but you should use a computer that exploits quantum mechanics. And the speed up for that is actually exponential. So by doing this, we hope that we can come up with new quantum chemistry protocols that will make drug design and other molecule design more efficient. This is there will be a long time until we see those applications, but they are proven to be exponentially faster. The other thing you can do Fourier sampling exponentially faster. So everyone knows that calculating Fourier transforms is a very useful protocol, and quantum computing provides something that is exponentially faster than the famous fast Fourier transform algorithm. And you can also solve linear systems. So you can diagonalize any kind of matrices, whether they're Hermitian or unitary or not. And you can invert matrices and you can solve differential equations, again, exponential speed up. So those are, in my opinion, the applications to quantum computing that are the most useful ones. There are many other applications. People are coming up with algorithms all the time, but those are certainly remarkably useful. So if you want more information about the status of quantum computing back in 2019, I highly recommend this paper here, because it tells you not just the great results, but also the challenges that lie ahead. So why are these algorithms faster? So often, and you see that quite often in the media, people talk about something called quantum parallelism. And I would like to give you a bit of a critical point of view on quantum parallelism. So I'm going to be a bit provocative here and say fantasy or reality. So I'll explain what I mean. The point is this: when you have a qubit, you have an infinite number of states, because these are continuous. These are imaginary continuous parameters. So the power of quantum computing is related to that, the fact that you don't have just 0 and 1, you have mixtures, and there's an infinite number of those, innumerable and infinite number of those. Now let's say you put n qubits in different superposition states like that. So what you get then is a superposition of 2 to the n inputs, right? Because you're looking at products of all these qubits. And now you have a state that has 2 to the power n bit strings, you see, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, and so on and so forth. There are 2 to the power n of them. Now you apply your quantum gates, you do processing. And what happens is that you're actually able to process all 2 to the n inputs in parallel. That's massive parallel processing. Massive parallel processing. Right? So this is the idea of quantum parallelism. So people tend to think that, in quantum computing, you are able to process data in a massive parallel way. That is true. However, the problem is that when you measure, only one of these 2 to the power n parallel computations is readable, because when you measure, you will collapse to one of these states, for example, this one. So only one out of the parallel processing jobs is visible. And that means that you cannot extract more information from a quantum computer than you can from a classical computer. So the thing about quantum computing is that you have to be very clever on how you construct your input and output. So you use interference of waves to actually construct outputs that have constructive interference at an output that you're interested in. And then you measure and you extract useful information. This can only be done for some tasks. Not all tasks are efficient in a quantum computer. Most of the tasks are actually the same complexity as in a conventional computer. But for those special tasks that I just showed you, you can actually do this. So I would like to show you my favorite quantum algorithm, and it's a quite remarkable one. It's called quantum phase estimation. And it's able to estimate the eigenvalues and eigenvectors of a unitary operator. You can do the same for non-unitary operators, but that takes more work. But the amazing thing about this quantum phase estimation algorithm is that it actually doesn't depend on the size of the matrix U that you're sampling the eigenvalues from. That's a remarkable fact. So if U is given, if you have U in your computer as a resource, the complexity of this algorithm only depends on the precision that you want to estimate the eigenvalues and eigenvectors. So what I'm saying is that, so the problem here is that you want to sample the eigenvalues and eigenvectors of U with precision epsilon. I'm claiming that the complexity scales as the logarithm squared of 1 over epsilon, where epsilon is how precise your sampling is. So how can that be? So I think that looking at this algorithm in detail is very useful to show you how where the power of quantum computing comes from. So what I'm trying to say is this. So let's say you have simple unitary operator, and the thing about unitary operators is that their eigenvalues are phases like this. So they can be written as e to the I times a phase. And in a quantum computer, you can represent that phase by this base 2 decimal representation. Now that's a perfectly fine representation for a number, but it's a base 2 representation. How can this be? How can this algorithm work? So let's say you input a superposition between the two eigenvectors of U, alpha U plus beta V. Now, first you apply, so this is the eigenvalue register that you use to estimate the eigenvalue. So what you're going to do is that first you're going to apply the so-called Hadamard gate to create a superposition. So this takes 0 into 0 plus 1 over root of 2. And then you're going to apply a control U operation. Now this control U, so the fact that you are splitting the state into 0 plus 1 over 2. So what it means is that the state here will be 1 over root of 2, 0, alpha U plus beta V plus 1, alpha U plus beta V. And then the control U, what the control U is going to do, the control U is going to apply the operator U to the part of the wave function that has qubit state 1. So it applies onto this sector. When you apply another Hadamard, you complete an interference pattern that is quite clever, because what you have here, the state that you have here is actually alpha 0 U plus beta 1 V. So when you read out this state, you will get 0 or 1. If you get 0, you immediately collapse this state to U. If you get 1, you collapse to V. So what this does is that this establishes, using interference and entanglement, it establishes a direct correspondence between the value of the qubit register and each eigenvector in your operator. That way you can prepare a state in a pure eigenvector without knowing what this pure eigenvector is. And you can also read out the value of the eigenvalue. And this is very scalable. And all this is done without any, irrespective of the size of you. So here's how you do this with more precision. And I would like to show you this on the IBM devices. So here is a 3-bit phase estimation of a particular operator that I want to show you now. So to do that, I'm going to a Jupyter notebook. You probably have seen this before. And my Jupyter notebook is connected to IBM. So what you do, you can go to quantumcomputing.ibm.com, and you can create an account. It's a free account. You don't need to pay for it. And they give you access to real devices here. So they already have devices with 127 qubits, but they are not public. They're only for certain premium users. But for the public, you have access to 5 qubit devices. So these are the devices. Those are real devices. They are inside a millikelvin fridge in New York State, and you can access them. And I'll show you how to do it. So here how to run this algorithm in IBM. So what I'm doing here, I am preparing. I'm pleased to share this Jupyter notebook with you. I'm looking at a 2x2 matrix, Ry of theta. That's a rotation about axis y. And I program in such a way that the eigenvalue is 0.01 equals a quarter. So the eigenvalue is pi by 2. The phase is pi by 2, right? So you can create the circuit here. There are commands to create it, and this is what I just did. So I just realized the circuit using their system. And then you can check which devices are available to you and how busy they are, so that you can submit jobs. This one here is particularly a good device. It's got quantum volume equals 32. It means it's low noise, and there are only 7 pending jobs. So if I have time, I would submit to it. It would take about 3-4 minutes for the job to be done. First, I ran a simulator. So this is a simulator that runs in a classical computer, could run in my machine. And as you can see, I got the right answer. 100% probability on the state 010. But then I ran into a real device. And what you see here is that you don't get just a peak at 010, you get other peaks too, because the devices are still noisy. However, you can clearly see that the main peak, the highest peak, is at 010. So in a way, the device is giving us the right answer. So we are in a time where devices are small and noisy, and we have to come up with techniques to mitigate the noise. This is one of the areas that I work with. I should mention that there's also the problem of converting this circuit into a circuit that runs with native gates in the hardware. And what I'm showing you here is the actual circuit that ran in this hardware, because the control U operation that I asked for was not available. They had to synthesize this operation using other operators. So you can see that there are many gates. This is the square root of NOT gate, square root of Pauli X operator. You see how complicated it is, and yet the level of noise is still quite satisfactory. So let me move back to my iPad here. So I don't have much time to describe my research, but I just want to say that I'm working on noise mitigation. And this is, for example, a paper that I just submitted with an undergraduate student last year, where we show how to post-process the data and reduce the impact of noise. This is based on a nice work that IBM showed where they would make their quantum chemistry calculations much closer to the exact result when they do this post-processing. Here we show that this post-processing can be done for any operation, particularly this is a 1 qubit operation with loss sphere. We're also interested in ways to benchmark the amount of noise, because the problem nowadays is that devices are noisy, and we want to find a way to not only compare the amount of noise in each device in a fair way, but also to diagnose where the noise comes from so that we can come up with strategies to reduce the noise in the hardware and the software. So again, this is another work that I did with an undergraduate student. And as you can see, as an undergraduate, you can do cutting edge research in that area. So I would just put my conclusions. I believe it's been about 47 minutes, but we can certainly discuss more research during our 30-minute chat after the talk. So I just want to say that quantum computers with 10 to 100 qubits can be built right now with different technologies. People are using trapped natural atoms, as well as artificial atoms made of superconducting circuits on a chip. And the public can access those devices and can run jobs in these devices. Quantum computers, they input superposition states, and they create entanglement and etc. And when they run, there is massive parallel processing, but only one of these processes are accessible during readout. And the thing here is that you need to construct clever algorithms that interfere in such a way that you extract useful information. And you should always remember, despite some claims out there, that quantum computers are not faster for all quantum computing tasks. They work in a particular way, so the quantum advantage is predicted only for a few important tasks, but these include factoring quantum simulations, Fourier sampling, and many others. Now, I would like to finish by asking the question, what can we do with a quantum computer of 10 to the 100 qubits without quantum error correction? Quantum error correction is able to remove the noise, but that requires a huge overhead in number of qubits. We need hundreds of thousands of qubits to run these algorithms in such a way that they show quantum advantage. But right now, the research question is, what can we do with those small devices, how we can control the noise? This is what we're working on, and I'll be glad to discuss with you research possibilities in my group. Thank you very much.
Thank you very much, Rogerio. Fascinating talk. We have a few questions, but I'm gonna ask one of my own right off the bat, because you mentioned about the need for a large number of qubits to be able to do certain useful calculations. Is there a kind of Moore's law trend for the number of quantum qubits with time that have been developed, and where is that going? What do you think in terms of the ramp up of the number of qubits that will be accessible to people on quantum computers going forward?
Yes, excellent question. Well, some companies do claim a Moore's law. IBM is claiming an equivalent to a Moore's law with their quantum volume benchmark. Quantum volume tells you not only how many qubits you have, but how noisy they are. You can think of it as the number of qubits times the number of gates you can apply until you lose coherence. So IBM is indeed claiming a Moore's law for their quantum volume. And I think I can see that this is happening because, I teach a course, Introductory Quantum Computing, here at UVic. And last year, I showed this 3-bit quantum phase estimation algorithm, and you could barely identify the main peak. Well, this year, I just showed you the results, and the peak is much more well-defined. So the noise is really going down fast. And the size of the quantum computers is also quite large. I mean, they claim that if you are an IBM Q-Hub member, Waterloo, Sherbrooke, and some other places in Canada are right now, you can actually have access to these 127 qubit quantum computers. Now, whether or not that's going to sustain to the thousands, tens of thousands, hundreds of thousands, well, that remains to be seen. Look, it is a high-risk research. We don't know if this is going to work, but we're working hard on it. And what I can say is that the progress is quite remarkable. These devices became accessible only 5 years ago, right? So.
Great. We have a couple of questions about encryption. I think I'm aware that classical encryption right now mostly involves factorization of primes, and you mentioned the classical the order of the speed of the process for classical and for quantum factorization. So one of the questions is at what number of bits do the two become equally fast? I couldn't do that calculation in my head there, and really at what point does factorization become faster with quantum in general than with classical factorization algorithms?
So I think the estimate that I heard is that you need a quantum computer with 1 million physical qubits, 1 million physical qubits, to break internet security, to break the 1024-bit, is it 1024-bit RSA, or maybe the 248-bit RSA? The reason why you need 1 million qubits is because you need error correction. The Shor's algorithm is very sensitive to noise. You need to do error correction. Now, this is a long time from now. I mean, I don't see this happening the next 5 years. We never know, right? Now, the point, though, is that everyone, there is already an expectation that this will be done in the future. And then people who are worried about security, they are worried about people saving data and then breaking the secret data, right? Reading the data afterwards, right? Because of that, there is already a movement in a strong activity in the cryptography community to devise the so-called post-quantum cryptography algorithms. Those are classical conventional algorithms that are not breakable by a quantum computer. So you can see that quantum computing right now is actually having an impact in society because people are already working to change the RSA security to a different system that is not based on factoring. So, I think, so the long story short here is that we don't know when such a 1 million qubit quantum computer will be available. But people are already changing the protocols.
It sounds to me like you're suggesting that for all of the motivation and use for quantum computing, sometimes we focus on encryption and security, but it might not actually be the driver in the near term, because for the advantage in quantum, we need quite a large number of qubits for the advantage for cryptography. But you've given us some ideas for other things for which quantum would become immediately better, or in the near future better. There's a question about quantum error correction. I think again, a kind of a two-part question. Is quantum error correction different from classical error correction, and how is it different? And more specifically, somebody's asking if you've looked into the connection between models of quantum error connection and the ADS/CFT correspondence.
Yeah, okay. So the first part of the question is how different is quantum error correction from classical error correction? So the answer is that there are some similarities. So classical error correction works like this. You take a bit and you apply redundancy. You copy that bit. So for example, instead of using 0, you use 0, 0, 0. Instead of using 1, you use 1, 1, 1. And then after the noise flips a few of these qubits, you do majority voting. So if there are 2 zeros and 1, 1, then 0 wins, you convert this to 0, 0, 0 again. Now, quantum error correction is kind of similar in that you entangle, you create a state that is a mixture between 0, 0, 0 and 1, 1, 1. But the thing is that you can't copy quantum information. You can't copy that, it's prohibited. And actually, this is why quantum information is so interesting for cryptography. Because you can show that this so-called no cloning theorem, you cannot copy the state of a qubit without destroying it. You can transfer it, you can teleport it, but you cannot copy it. So what you have to do, you have to exploit entanglement to add this redundancy. So in that way, it's, there's a similarity here because you are using redundancy, but you are using redundancy in a very subtle way because you're creating an entangled state. And then when you measure, you have to do the majority voting by looking at correlations between the qubits so that you don't flip the state of the qubits when you do this, when you do the readout to decide how you're going to correct. So the answer to this is, first of all, when quantum error correction, it looks impossible at first because of the no cloning theorem, but the way you do it is that you exploit entanglement. So it's very different from how you do classical error correction. But the principle of redundancy and majority voting, in a way, it's kind of there. I hope I answered the question. I don't have a slide here, but it's a very beautiful theory. Yeah.
The key is also that it is different. So that's interesting.
Yeah, it uses entanglement. It kind of, so back in 1996, before 1996, when quantum error correction was not invented, people were sure that it would be impossible to do error correction, therefore quantum computers couldn't ever be built. So it was very surprising when people discovered quantum error correction. And the key is entanglement. Entanglement is not an obvious thing. Now, the second question, it's the relation to ADST correspondence. So that is an area that I'm not very familiar with. There are people exploiting these deep correspondences, because after all, quantum computing is quantum theory of two-level systems, right? But I'm not an expert in this area, so I prefer not to answer.
Okay, thanks. You presented two examples of how to do quantum computing, one with trapped ions, the other one with Joseon junctions or superconducting circuits, I guess. What are some other ways where we might achieve quantum computing? There's a question specifically about maybe BEC could be used for that. What are some of the ways that we're looking at that aren't just ions or superconducting circuits?
So there are a lot of proposals. I do believe there are proposals with Bose-Einstein condensates, but I think the Bose-Einstein condensate is not a very, it might be difficult. In a way, you should think of superconducting qubits as kind of like a Bose-Einstein condensate, because the superconducting state is in many ways similar to a Bose-Einstein condensate. The macroscopic quantum coherence in a superconducting circuit is very similar to a Bose-Einstein condensate. It's a condensate of Cooper pairs. So the Bose-Einstein, so if you can make a Bose-Einstein condensate, use BEC as a quantum computer, the sort of methods you're going to use are very similar to the superconducting qubit methods. Okay, you can have the equivalent of a Joseon junction in a Bose-Einstein condensate. It's just a gap, right? Now, there are many proposals. Let me just emphasize a few of them. Photons are very promising. So this is something I didn't talk about. So right now, there is a lot of activity, and there's even a company in Canada called Xanadu, based in Toronto, who's doing amazing progress on this. People are looking at photonic circuits. So the way they do quantum computing is very different, and I think it's very interesting. You basically create a state of interacting photons, and then you measure. And by measuring, you apply the gaze. And that is, first of all, it's super fast, right? Because photons, optical photons have a very large frequency. And photonic technology is very well developed. So there, photonics is a great proposal. Semiconductors, spins in semiconductors. In fact, I did my PhD on that a long time ago. So the spins, impurity spins, like phosphorus in silicon, those are extremely high coherence. And silicon technology is well developed for information technology. So that's another very promising way. The only thing is that those systems have not scaled up yet, but I'm sure they will. So I think, think of cars 100 years ago. How did cars look like? Do cars look the same nowadays? Well, no. So that's a good analogy to think about. I think in 20 years, the quantum computers we may be talking about are totally different than these. We should be open-minded about other technologies.
Well, thank you, Rogerio. We're coming up on an hour here, so that brings an end to our question period. I'm going to turn it over now to Bill Whelan, who's going to wrap up the public portion of this, but thank you again for a great talk.
Thank you, Aaron. Pleasure.
That's great. Thank you, Professor Slipkoff. I'm Bill Whelan, a Vice President-elect of the CEP. At this time, I would like to thank a number of people who helped to organize today's talk. First of all, CAP Regional Coordinator, Dr. Jesse Heilman from Carleton University, who greeted you at the start of the talk. Francine Ford, Alicia Forgy, Vicky Van Massenhoven, and Jenny Cleaver in the CEP office. I'd like to thank our host today, Dr. Aaron Slipkoff from Trent University. And a big thank you to our speaker, Dr. Rogério de Sousa, for giving us an excellent, informative, and engaging presentation. Thank you, Professor de Sousa. And thank you all for participating. The sixth talk of the 2022 CAP lecture series will be by Dr. Ozzy Mermut on Friday, April the 1st at 2 p.m. Eastern. Dr. Mermut will speak on biophotonics, shedding light on biosensory disorders and age-related degenerative diseases. We really hope that you can all attend. And as a reminder, all participating students are invited, all participants are invited to remain to have informal discussions and conversations with Dr. de Sousa in a Zoom breakout room. You should see an option to join the breakout room at the bottom of your screen shortly. So on behalf of the CEP, thank you very much for attending today's CEP lecture series talk. We hope that you will stick around and have continued discussions and engage with Dr. de Sousa in the breakout room. Thank you all again for attending, and have a